Mr. Tarou, in this lesson, we're going to be taking a look at yet another test for convergence. We have a direct comparison test to help us to determine if a series converges. And it says here we have if a series A sub n looks to converge, then we're going to choose a new simpler series, series B sub n, such that A sub n is every term, the A sub n expression in our first original series is going to be greater than 0. So we're not looking at like alternating series or something like that. We have 0 is less than A sub n, which is then less than or equal to B sub n, the general term of the new series that we've come up with. And the series B sub n, the new one that we come up with, must converge. So we've learned about p-series test, geometric series, telescoping series, we've done the integral test, and we're starting to gain some experience with a given series, and hopefully we can kind of look at it and start to judge if we believe a given series, converges. If we believe a given series converges, yet it would be hard to prove that, we're going to come up with a new series. It must also converge, and after a given point, a given value of n, B sub n, the general term B sub n, is going to be equal to or greater than our general term of the original series. And this kind of like as an extension, think of the squeeze theorem. If we want to prove that the limit as x approaches infinity of the sine of x over x, we should be able to look at this and go, well, the numerator of this fraction is not constant, but the sine of x never goes above 1 and below -1, where our denominator is increasing without bounds. So it looks like this limit should be 0, but can we prove that without any doubt at all that this limit actually is 0? Well, with the squeeze theorem, since we believe it's 0, but we can't really prove it, because the trig is kind of weird sometimes. Sometimes, like if you graph the sine of x over x, maybe you get a hole in the graph instead of a vertical asymptote, so they can act a little bit weird when x is 0 anyway. So we would say, well, we know sine stays between -1 and +1. Let's say that -1 is less than or equal to the sine of x, which is always going to be less than or equal to 1. And we know that without a doubt because we know what the parent function y equals sine of x looks like. So we know that to be true. So therefore, if we divide each part of this compound inequality by x, so we have -1 over x is going to be less than or equal to the sine of x over x, which is then going to be less than or equal to 1 over x. And we know we don't need to change the direction of these inequalities because the question is letting x approach positive infinity. So I'm dividing each part of this compound inequality by a positive number. That's not going to change our signs. And now below, always below or equal, and always above or equal to the sine of x over x, we have -1. Y is equal basically to -1 over x. That was a parent function in pre-calculus. It's a reciprocal function. So we can say without a doubt that the limit as x approaches infinity of -1 over x, we know that's 0. We know that reciprocal function with just a transformation of a reflection over the x-axis is approaching 0. That sort of horizontal asymptotic behavior that we talked about in pre-calc and algebra 2. The limit as x approaches infinity of 1 over x is also going to be 0. And so our more complex function of sine of x over x is always going to be greater than or equal to -1 over x and always less than or equal to 1 over x. Thus, by the squeeze theorem, the limit as x approaches infinity of the sine of x over x must be equal to 0. That's the extension of the squeeze theorem is kind of what's happening here with the direct comparison test. If we have an A sub n that looks to converge, but it may be a little bit too complicated to easily prove that, if we come up with a new series based off of B sub n, and if B sub n gives a few initial terms or values that are smaller than A sub n, it's okay as long as after some value of n, our general term of b sub n goes larger and then stays larger indefinitely as n goes to infinity, yet we know that that series based on b sub n converges, then basically by the squeeze theorem, we're proving that our given series converges by the direct comparison test. And if we look at our original series and we believe it to diverge, then we're not squeezing towards zero, but we have to come up with a new series that is going to give individual terms at a point that are always basically less than or equal to a sub n, which then also diverges. And so that divergent series that's always below what we believe to be a divergent series, it kind of like keeps that series up and shows by the direct comparison test that that series does indeed diverge. So we're going to attempt to do that with 4 examples. And our first example here is the series where we have n starting to, at 1 going to infinity of the natural log of n over n. Well, the numerator here, if we think about what the graph of y is equal to the natural log of, let's say, x looks like, that's a function that grows very rapidly early on, passing through the value of 1, 0. But then it sort of leans over and starts to grow very, very slowly, almost like there's a horizontal asymptote, almost like the natural log, becomes almost constant, but we know that there's no horizontal asymptotes for the natural log of x. But the admission, the understanding that it starts to grow very slowly as x increases means that this kind of almost acts like a constant. It doesn't, but almost. So we're going to compare this series to our famous harmonic series, which diverges, compared to this divergent harmonic series. You don't even have to prove that. It's just a known fact. So we need to show that this new general term is going to be less than this general term at a point. Now, the denominators are already the same, so let's just focus on the numerator. We need the natural log of n to be greater than 1. And when does that occur? Let's get rid of the natural log by making both sides in power of e. Then we have n is greater than e, or n needs to be greater than or equal to, since e is 2.718. The numerator, natural log of n, will be greater than 1 once n is greater than or equal to 3, since the domain of, we're starting at 1 and counting up by integers. So since we have shown that at some point the natural log of n is going to be greater than 1 off that condition, therefore the natural log of n divided by n is going to be greater than or equal to 1 over n, again for that n is greater than or equal to 3. We've already made a statement that this series, that after n is basically after 3, this divergent series is always smaller. So therefore, by the direct comparison test, the given series diverges. So we can see the direct comparison test, it can go quite quickly, and it might be a test that you really want to use a lot. However, if you can't hypothesize the convergent divergent behavior of your given series and then quickly come up with an appropriate comparative series, it can be quite a difficult little test to figure out, and it takes a lot of experience to really get good and quick at it. I might even say that the direct comparison test is not my go-to test. If I can do like a ratio test or a limit comparison test, I might lean towards that first, even though that example went quite quickly. And some of these examples will go quickly, but you might find it cumbersome at times to figure out a good alternative series to come up with to prove your convergence or divergence. For our second example, we have the limit or summation where n starts at 0 and goes to infinity of 1 over 5 to the n plus 2. Well, if you think about back in Algebra 2 and Pre-Calc when you were looking for asymptotic behavior and letting, say x go to infinity or negative infinity, we remember that it was the terms with the highest powers that had the most control as some variable goes off to infinity. So as n becomes very, very large, the effect of this little plus 2 that we have in the denominator is going to have very little effect. Now, that means understanding that behavior of functions as, the independent variable goes to infinity, we can come up with a comparative series, which is 1 over 5 to the n. And I believe, if I just kind of ignore that plus 2, this kind of looks like a familiar series, and I believe this is going to converge. So I need to come up with another series whose general term at some point gives larger answers. So we're going to compare this to the series where we have 1 over 5 to the n, which means that is going to be equal to the series, of course, 1 to any power is 1, so that could look like the summation of 1 over 5 to the n power. Well, a fixed-based variable exponent means that we're looking at an a sub n, which now is a geometric series. This is a geometric series with r being 1/5, therefore it is convergent. Now, this being a convergent series is not going to be helpful to prove that this series converges unless this new series has general terms that are always larger. So let's kind of show that, like we did with our squeeze theorem. We have this denominator of 5 to the n is when n is basically a positive integer or greater than or equal to 0. 5 to the n is going to be less than or equal to 5 to the n plus 2. So this denominator is smaller than this denominator. Thus, when I take this larger value and place it under 1, and this value and place it under 1, of course, because that's our numerator, this smaller denominator is going to make what? A larger overall fraction. So since 5 to the n is less than or equal to 5 to the n plus 2, therefore, 1 over 5 to the n is going to be greater than or equal to 1 over 5 to the n plus 2. So, and that's going to be for basically all values of n greater than or equal to 0. So this new series that we've come up to compare it with our original series converges and is, for every value of n, going to yield a larger individual term that's getting added up in the series. So therefore, by the direct comparison test, the given series converges. And for our example over here, we've got that same idea that our numerator is a constant and our denominator has a variable base. Over here we had a fixed base, but it had a power of n. We have a variable base of n, and yes, there's a plus 1, but as n goes large, that plus 1 is going to have less and less influence over what this overall value that we get from this general term is going to equal, and that n to the 5th to the 1/3 power is going to take over. So we're going to compare this to the series where we have 2 over n. N has got a power of 5 and a root of 3, so it's going to be n to the 5/3 power. And just for note's sake, we can move this 2 out front and say we have 2 times the sequence or the summation of 1 over n to the 5/3. This is a convergent p-series with a p-value of 5/3, which is larger than 1. So once again, we've come up with a simpler series that converges. Hopefully, that's going to show that this given series converges because this term is always giving individual values after some point that are larger than this general term. So we have n to the 5/3 will indeed be larger, greater than or equal to n to the 5th plus 1. Actually, excuse me, smaller. To the 1/3 root, right? We have n to the 3rd root then being written, actually, let's do this. Let's do this as n to the 5th then being raised to the 1/3 power. That way it's really, really obvious. So if we take a value and we raise it to a 5th power and then to the cube root, that is going to obviously be smaller, I hope it's obvious, than that same number raised to the 5th power and then plus 1 before taking the 3rd root. So this term is always smaller than or equal to this term. Now let's put that under 1, and so we have 1 over n to the 5th to the 1/3 power is going to be greater than or equal to 1 over n to the 5th plus 1 to the 3rd power. And of course, there we have a 2 in this numerator, but we can just move that 2 out in front of the summation notation. So therefore, by the direct comparison test, the given series converges. Let's take one more example. So for this example, we have the summation where n starts at 0 and goes to infinity of 1 over n factorial. So it's our first example with a factorial and is the last example in this video. We need to come up with a series to compare this to. Well, this is not quite as obvious as our previous 2 examples because there's no fixed power. And then it might be a little bit trickier to come up with a simpler series. So what is the behavior of factorial, right? If you expand this out, we're going to have 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on, which means that we're looking at, well, 0 factorial is defined to be 1. So we have 1 over 1 plus 1 factorial is again 1, plus 1 over 2 factorial is 1 times 2, plus 1 over 3 factorial is 1 over 1 times 2 times 3. Let me do one more. Plus 1 over 4 factorial, which is going to be 1 over 1 times 2 times 3 times 4, and so on. So our denominator is being created by a repetitive multiplication of factors. So what math operation do we know that shows a repeated multiplication of a factor? Powers. So let's take a look and compare this series with this series, where n starts at 0, goes to infinity, of 1 over 2 to the n. Now, how am I coming up with this? Because 2 to a power of n, as n goes to 0, 1, 2, 3, 4, 5, if n is 4, that's going to be 2 times 2 times 2 times 2. We're going to have repeated multiplication in our denominator of each of these terms if I were to expand it, just like we have with our factorial. And this is, of course, again, a convergent geometric series with r being 1/2, which the absolute value of 1/2, of course, is less than 1. So is this convergent geometric series going to help us to show that our original series converges? Only if, that will be true, that will help only if each general term in our new simpler series at some point, after some value of n, starts to be larger than we get from 1 over n factorial. Now, if we expand this out, when n is 0, we're going to get 1 over 1, plus when n is 2, we're going to get 1 over 2 to, 1, excuse me. When n is 1, we're going to get 1 over 2. Again, 0, 1, and then when n is 2, we're going to have 2 squared is 4. So far, this first denominator is 1, this first denominator is 1. The second denominator is 1, this denominator is 2. This denominator, the third denominator is 2, my third denominator is 4. So far, my new series is giving me smaller values, smaller individual terms, not larger. But if we go n is 0, 1, and 2, when we get to 3, we're going to have 2 cubed is 8, so we have 1 over 8. So n is 0, 1, 2, and 3. So this is 1/6 and this is 1/8. Oh, wait a minute. This is 1/6 and this is 1/8. Okay, let's go one more time. Let's let n be 4. 2 to the 4th power, 2, 4, 8, 16. So we have 1/16. And up here we have 1 over 2 times 3 is 6 times 4 is 24. Okay, so once we get to n is 4, 1 over 24 is smaller than 1 over 16. And then to get the next term, I'm going to multiply the denominator by 2. To get this next term, I'm going to multiply the next one by what? 0, 1, 2, 3, 4, 5. So for this next term, I'm going to multiply the denominator by 5. Where down here, I'm still multiplying by 2. We can see here that when n is 0, 1, 2, or 3, 2 to the n is smaller than or equal to 1, 1, 2, and 6. But once we get to 4, 2 to the n is giving a smaller answer than n factorial. So 2 to the n is less than or equal to n factorial for n greater than or equal to 4. So therefore, 1 over 2 to the n is going to be greater than or equal to 1 over n factorial for n is greater than or equal to 4. Therefore, and we've already stated that our new series is a convergent geometric series. So therefore, the given series, which of course is that summation where n starts at 0 and goes to infinity of 1 over n factorial, converges by the direct comparison test. And that is the end of my last example. I'm Mr. True. Bam! Go do your homework.